This was 36. There's a special name for this diagram. It is B36. This is B. What will this be then?
D42.
This is D42. D stands for divisors. These divisors, the set of divisors, 1, 2, 3, well, that's not, there's a nicer way of saying it. Let S be equal to N. Now, that's a better one. D divides 36. You are familiar with this symbol? D divides 36.
Yes, sir.
Yes. D divides 36 means 36 equals B times some integer k value. So 1 divides 36, 2 divides 36, 3 divides 36, and so on. So these are the integers that are the divisors of 36. It turns out they form a partially ordered set where A less than or equal to B if and only if A divides B. That is when you connect something. Yes, 1 divides 3. So 1 is less than or equal to 3. We can. Now this diagram is clear. Ruhi tells me you have all completed this.
Yes, sir.
In both these diagrams, you will notice something else. You see, you can reach 42 if you follow this path. Agreed? You can also reach 42 through other paths. But let's look at this one. 1, 3, 21, 42. There's something interesting about this set of numbers. A less than or equal to B. Is this a partially ordered set? It turns out it is. 1 is less than or equal to 3. 1 is 1 less than or equal to 1? Under this definition, yes? Is 1
Yes.
less than? It is. So the reflexivity is achieved. A less than or equal to B if and only if A divides B is the condition. Then 1 is less than or equal to 1, therefore we have reflexivity. 3 is less than or equal to 3, and so on. And if 1 divides 3, implies 3 does not divide 1. Agreed?
Yes. Yes.
Yes. Therefore, there is no question about AB and BA appearing together, right? Because if both of them are in R, what condition has to be obeyed? Anti-symmetry says what?
Sir, that two numbers,
This will,
two
yes,
elements in the set cannot be reversed and placed.
yeah, if AB and BA are in R, then A has to be B. Therefore, if A is not B, then it is both AB and BA not in R. Do you agree?
Yes.
Because what if they are both in R?
Then it will be symmetric.
Then A has to be equal to B.
A is equal to B.
Yeah, but we said A cannot be. If we start with A not equal to B, then we cannot have this flip. And it doesn't flip here because 1 divides 3, 3 doesn't divide 1. So anti-symmetry is satisfied. Agreed?
Yes.
And is transitivity satisfied? Transitivity is
Yes,
usually
it
satisfied.
is.
Yeah, 1 divides 3 and 3 divides 21, 1 divides 21. Well, actually, let's prove it another way.
Sir,
Let's prove it another way. Suppose A divides B and B divides C. Can we prove that A divides C? Let's see. What does A divide B mean? That means B equals AK for some integer. Agreed?
Yes.
And what does B divide C mean?
C is equal to B multiplied by some integer.
B some L. Agreed?
Yes.
Well, if C is BL, then we can write substitute for B, can't we? It is AK. So C equals AL, so A divides. If C equals A times an integer, then A divides C. Agreed?
Yes.
Yes.
Which is what we wanted to prove. Can we take this out of here?
Sir, just reminding you, in case you wanted to save the previous work, you can always take
Yes. Okay. So A divides C. Let's take this. Thank you, Ruhi. Let's take this. Good. Oh, I need this. I'll go back. Good. So we have just proved that this subset of the divisors of 42 is a partially ordered set by itself. But this subset, this partially ordered set is nicer. What is nice about it? What is nice about this partially ordered set?
A, B, and like C and D, like it's transitive till D.
It is transitive. Not only that, every element is related. Every element is related because if you find two elements here, that means the lower one divides the other one. Is that true?
Yes.
So in this, they call it a chain. A chain is a partially ordered set in which every element is comparable. You can compare it. A less than or equal to B for all A, B in the chain. And we will come to that a little later. So I will now go to a slightly different thing. The other day we said, if you take a set S, then you can form S cross S, the Cartesian, they call it, although I say S cross S, it's not really S cross. To say it quickly, I say it, that's all. This is called the Cartesian product. Cartesian. You heard the name Descartes, right? That is, he is the one who came up with the idea of and what is this point? If this distance is x, this distance is y.
X comma Y.
X comma.
This idea was from Descartes. That is why they call it the Cartesian plane. In the Cartesian plane, you take the x coordinate and the y coordinate. That is where the Cartesian product comes from. If you take a set S, let's for example take the set just A, B. What is the Cartesian product of S with S? It will contain pairs. How many pairs are there from S? I will continue to say cross S. How many pairs? A with A. You can pick A from S. You can again pick the same A if you like. Then you have A with B. Tell me. Are we done? We only picked A from this S. What else can we pick?
B comma B.
B comma, how about B comma A? I'm not talking about the partial order yet. Right now I'm talking about the Cartesian product and B comma B, isn't it? This is the Cartesian product. Now the partial order is a relation, a particular relation. You see, any subset of the Cartesian product is called a, why do we denote it by the letter R? R to remind us that it is a relation. A relation is any subset of the Cartesian product of S with S. This is why how many elements does this Cartesian product have? This has how many?
2.
This has how many?
4.
This is one element because it is, these are, the elements of this are what? Pairs. If I had, I could also have, it doesn't have to be S with S. If I had another set, you can have a Cartesian product of one set with another set, just like X here and Y here. But only when this is also S can we talk about partial orders. But even if this was T, we could have relations. Now, how many subsets this can have, this set has?
2 subsets.
How many subsets can this set have?
16.
It can, okay, first of all, you start with the set that contains nothing. Agreed?
Yes.
That is a subset of every set. Hey, do you know something amazing? There are all kinds of sets in the universe. Uncountably many subsets. But there is only one empty set. That's very exciting. I didn't know that. First time, there were a few things that I learned that excited me. One of them was this. There is, you can have a set X, set Y, set R, set S, all kinds, but there is only one empty set. And let me show you why. Empty set is contained in every set, right? Empty set is a subset. Empty set is a subset of a empty set is a subset of every set. Okay? You give me a set S, then the empty set denoted by the Greek letter capital P is contained in S. Now, if empty set is contained in every set, suppose there are 2 empty sets, then because this is a set, phi will be contained in phi prime. Do you agree? If this is the definition of an empty set, it is contained in every set. There's nothing in it. It is empty. If it is in every set, can there be 2 empty sets? Well, let's suppose there are 2 empty sets. I call one phi, the other one phi prime. Because this is a set, can't I say this? It is a subset of every set. Here is an empty set. Here is an empty set, but the empty set is a set. So I can say that this is contained in this. But phi prime is an empty set, you are saying. And this is a set. So that is contained in phi. What does that mean? If a set A is contained in a set B, and B is contained in a set A, what does that mean? A equals
B.
That is the way you prove the equality of sets. Therefore, phi equals, there is only one empty set. Empty set is unique. Now, let me. So we said, I'm going to stay on this until you understand this. S cross S is, oops. Now, let's find all the subsets of this. The first one is the empty set, which we call by this name. Then we can have just this element. There is another one will be just BB. Another one will be AB. Is this a subset of this set? Remember, this set has how many elements?
4.
This set has 2 elements. This set has
4.
4 elements. These elements look funny. Why? Because an element doesn't mean it has to look like this. This is a different set from this. An element in this set looks like this, not like this. Hey, suppose you had STU. What will an element in this one look like? X, Y, Z, wouldn't it? One from each. Another one will be, I don't know, X1, Y1, Z1. See, the more you add, the elements will have more elements. These are triples. These are pairs. These are pairs because you have only 2 sets here. Let me go back. So, hey, wait a minute. Just like you have done this before, you did a homework like this. You have, from 4 elements, how many subsets can you make? The empty set.
2 to the power 4.
Didn't you do this?
Yes, sir.
Okay, give me another subset of this.
XY.
XY. Give me another one.
XZ.
Are we done?
No. We need
X is done. Y.
YZ.
YW.
O. YW. Are we done?
W.
ZW.
ZW. Are we done?
No, that.
We are done with pairs.
Sir, then XYZ,
XYZ.
XYW,
XY. XYW.
XZW,
XZW.
and YZW.
YZW. Are we done?
We need to take the whole set also, like the subset of the whole set.
Right.
XYZW.
So how many subsets this set has?
2 to the power 4.
Yeah. See, we are looking for subsets H. See this equal sign? So if this is the set S, it itself is a subset of it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. is set with 4 elements has how many elements? How many subsets?
2 raised to 4.
Power
2 to the
4.
4. The reason is you can make these subsets by this device. Imagine you have 4 positions. If you put nothing there, what do you get? Which set do you get?
Empty.
Empty set.
If you put 1 here and 0, 0, 0, what do you get? X.
X.
So let's say this is X, Y, Z, W. If you put 1, 1 here, what do you get?
XY.
If you put 1 here too, what do you get?
XYW.
Yes. So you see, all the subsets can be generated by filling positions, these positions, X, Y, Z, W. Another way of saying is that these are the binary strings. How many ways can you fill here? Oh, 2 ways. How many ways you can fill here?
2. 2
The total number of ways you can, total number of strings you can get is 2 times, tell me.
2 times 2 times 2 times
2
2.
times 2 times 2 times 2.
That is 2
2
to
to
the
the
power
4.
4.
So you see, that is how come a set with a set with 4 elements has 2 to the 4 subsets. Now, if you start with just AB, Cartesian product of S with S will be A comma A, A comma B, B comma A, B comma B. This is a set with 4 elements. How many subsets it has? How many subsets this set has? Just like X, Y, Z, W has 4 elements, and that gave you 2 to the 4 subsets. How many subsets this set has?
4.
2 raised to 4.
2 to the 4, because it has 4 elements. The elements of this set are pairs, whereas the elements of this set are like AB. Is this distinction clear?
Yes.
Yes.
Cartesian product of S with itself consists of pairs. And out of this 2, you can get 4 pairs. And that means this set has 4 elements. That means it has how many? This set has how many subsets? Okay. Out of those, something funny happens. All those are, you have 16 relations. Out of that, the partially ordered relations, there are only 3. Let me show them to you. So if S equals AB, first of all, I need to have There is one. I'll show you why these are the only ones. You will be happy in a couple of minutes. Don't worry. Okay. There are 16 subsets you can make out of this. Are you happy with that? There are 16 subsets you can make out of this. Agreed?
Yes.
Every subset of S cross S is called a relation. But out of those 16 subsets, only 3 are partially ordered sets. Let's check it out. Is this a partially ordered set? Is it reflexive?
Yes.
Who else agrees? Let me have some more people. Is this set reflexive?
Yes.
If A is related, A has to be less than or equal to A, right there. Right? B less than or equal to B. Is it reflexive?
Yes.
We will say A less than or equal to B if and only if A be in this set. This is a relation. Okay, reflexive, is it anti-symmetric?
Yes.
The first one isn't.
Well, do you have an AB and a BA? Do you have an AB and a BA? No.
No, so it's not anti-symmetric.
So it's okay. If it is there, then A equals B. Agreed?
Yes.
It is not there, so you don't have to worry about it. Yes or no?
Yes.
If AB and BA are both there, then you will know. In fact, in a partial order, we said earlier, this cannot happen. Only one of them can appear, or none of it. Neither of them appears here, so that is okay. And is it transitive? What is transitive? A less than or equal to B, B less than or equal to C implies A less than or equal to C. First of all, we don't have an A less than or equal to B, do we? We only have an A
No.
less than or, right?
Yes.
Yes.
There is, you see, we only have an A less than or equal to A, and we have a B less than or equal to B. We cannot connect to them. So we don't have to do any work. It's transitive. Let's check this one. Is this set reflexive?
Yes, it is.
Is this relation reflexive?
Yes.
Yes.
And is it anti-symmetric? Oh, wait a
AB
minute.
and BA don't exist.
AB is there, but is BA there?
No,
No.
it is not. That's
So we are okay. If BA was there, then A is equal to B. So is it anti-symmetric?
No.
Because it doesn't violate it, right?
Yes, sir.
If AB and BA are there, then we have to make sure that A equals B. Only A. How about this one? How does this relation differ from this relation?
Sir, A, B has changed to B,
Instead of AB, you have
B comma A.
B comma A. So, the So what did we do so far? Let me see. I have a set S, just two elements. I am going to draw a Hasse diagram of this, a picture. There is A, there is B. I wonder what the Hasse diagram of this is. Anybody can draw here? A comma B means A less than or equal to B. A comma B means if and only if A less than or equal to B. Yes. Can you draw the Hasse diagram of this relation? This partially ordered. This is a partial order on this set.
Yes.
How about this? Suppose I drew this. This will be B. This will be
A.
How about this one? Will it have the same shape? A here? No. B here and A here. Whew. It is simple, but we found that out of the 16 relations possible on this set, only 3 are partial orders. You see, first of all, how do you know there are only 3? Anyone? First of all, we must have all the reflexive relations in it. So we must have these 2. And then you see if you can add any of these guys. Can you add both of them? Can you add both of them?
No.
Because if you add both of them, it will not be anti-symmetric, would it? If you add both of them to this here, would it? It would not be anti-symmetric because we assume A not equal to B, right?
Yeah.
So we can only add one of them, and I did. And then you make another one with the other one. So there are only 3 partial orders on this set. Okay. All right. And that's right. Now, out of this, let me now go to another before I okay. If you take a set S, there are 3 interesting relations on it I want to talk about before I go to the next topic. One is the identity relation. That is, from S I go to S cross S. In S cross S, I have all kinds of A's and so on. Identity relation consists of XX, where X comes from S. Identity relation means just the reflexive ones. This is a partial order or not. This is a partial order on any set. Is it reflexive?
Yes.
Is it anti-symmetric?
Yes.
Why?
Because there's no.
There's no other element to compare.
Yeah, there's no.
This situation doesn't occur, right? It's all x-axis. This is anti-symmetric. Agreed?
Yes.
And is it transitive?
Yes.
No.
Well, let's see. X. Can I have an XY?
Then it's transitive.
Yeah.
Yes. But is there an element like this there in this relation?
No.
No.
So if there is one, then XY. Well, even then XY. But there is no XY in here, right? If this, then this. So I don't know if I confused you there. You see, this identity relation has only this. So there is it is reflexive, it is anti-symmetric and transitive, it's a partial order. It violates none of the conditions. Agreed?
But it isn't transitive, right? X-axis is the only term.
That's right. There is if XX, XY, then, but there is no XY. Agreed? So if there is,
Yes.
the only Y you can put there is what? X. And then of course it is correct. So is it transitive? Remember, if XX and XY, like actually what is the, let's make it even more interesting. AB, BC implies AC. Let's apply this to this set. A comma what? What do I write? A comma
A.
A. Well, if this is A, this has to be also A, right?
Yes.
If this is A, what should this be?
B.
If this is A, what should this be?
A.
A. You see, this condition becomes just this trivial thing. It's trivial. It's trivially satisfied. So this is a partial order. Think about it at home. Then there is the whole, we are almost talking philosophy here, aren't we? How about this? Is that a relation? Is this a subset of S cross S? What is a relation? Any subset of S cross S is a what? Relation
Relation.
on S. So if any subset of S is a relation, then this whole thing is a relation, isn't it? Suppose you take a set, let's say G, a set G. Is G a subset of G? What do
Yes.
you mean by subset? What do you mean by subset?
Like that
Any
whole thing is in the main set.
A is a subset of B if and only if X contained in A implies
X contains in B.
X contained in B. People who live in Mumbai are people who live in India. This set of people who live in Mumbai is a subset of the people who live in India. Agreed?
Yes.
X contained in A implies X contained in B. Now, since any subset of S cross S is a relation, S cross S itself is a relation. Agreed? Because every subset of S cross S is a relation. This is it is difficult for you to grab onto that, but you will. I'm writing again. What am I saying? Every subset of S cross S is a relation on S. Take this as the definition of a relation. This will be in the notes, guys, okay? Now, if every subset of S cross S is a relation, is S cross S a relation then? S cross S, is it a subset of S cross S?
Yes, it is.
It is. Because what is the definition? How do you check if A is contained in B? X contained in A implies?
X contained in B.
So, is this a subset of this?
Yes.
So, if every subset of this is a relation, is this a relation?
Yes.
If this is a subset of this must be a relation on S, isn't it?
Yes, it has to be.
Yes or no? If every subset of S is a relation, and since this is a subset of this is a relation on S. Yes?
Yes.
That is called, such a relation is called a universal relation. On the set S. Unfortunately, it is not a partially ordered set. Can someone tell me why the universal relation is not a partial order?
Because there is A, B and B, A both in it.
Yeah, because in a universal relation, A, B and BA and all, everything is there, isn't it? Therefore, a universal relation is not a partial order. Is this clear? Is this clear?
Yes.
In S cross S, if A and B are in S, A comma B in S cross S, B comma A in S cross S. So if you take S cross S as the whole relation, then both of these are there. So we cannot have anti-symmetry if we use this. The universal relation cannot be, is not anti-symmetric. Do you see that? Universal relation is not anti-symmetric. Therefore, universal relation is not a partial order. And finally, before we leave this philosophy, suppose you have a set S. Is the empty set contained in S?
Yes.
Yes.
Now, the question is there a partial order on Let me see. Now, let me do it another way. Suppose we take S as the empty set. S is the empty set now. There's nothing in it. Is there a partial order on S? What is? Let's check reflexive. For all X in S, X in the relation. Is there a partial order R on S? Is this true? Is there any element in a set like this? Is there any element in the empty set?
No.
So, is this statement true for the empty set or for the relation?
No.
Let me think here. For all X in S, since there is no X in S, this is not violated. There is nothing to violate this condition. There is no X. For every X in S, this is true. Because there is nothing in there. This is vacuously, trivially true. Usually, guys, if it is not violated, it's okay. For every X in S, this is true. Like, that is false. False implies true. So it is reflexive. I will stop with that. It is anti-symmetric again because it is transitive. So there is a empty set has a partial order. So let's go away from here to the next topic. What time is it? Oh, I had to be careful. Total order. Next topic. We are leaving partial order. I told you a little while ago, if you take the good. That's the first time I do this, guys. If you take the divisors of 42, 1, 3, 21, 42, 1, 3, 21, 42, every element is a divisor of things above that. Is that true? Every element here is a divisor of an element above it. Each element above it, isn't it? 1 divides 3, 1 divides 21, 1 divides 42, 3 divides 21, 3 divides 42, and so on. You see a chain like this. A, B in the chain, call this a chain. I can say that A is related to B. That is called a total order. So I can now go back and go like this. Total order is total order on S. On S. A total order is when a relation R on set S is a total order if for all A B contained in S, either, let me see, let me check if I got this right. I have a small doubt now about total order. Total order. On a set. In a relation. Yes. If for all AB in S, either A less than or equal to B or B less than or equal to A. Let me check if that is correct. Yes. So I said over here 1, 3, 21, 42. Yes. 1, 3, 21, 42. Let us take our S is 1, 3, 21, 42. Is this true? Is every element related to the other element? 1 less than or equal to 3, great. Is 21 less than or equal to 3?
No.
Is 3 less than or equal to 21?
Yes.
Why? Notice how I write the less than or equal to. Because that means 3 divides 21. Right? This is that chain from D42, where we had 1, 3, 21, 42. Is 42 less than or equal to 3?
No.
So, but what can you say?
3 is less than or equal to 42.
42. So if you take any two elements here, is this condition satisfied?
Yes.
So that is why this is a total order. Let me take another example. The most important example. The natural numbers are 0, 1, 2, 3, so on. We will say A less than or equal to B if and only if A less than or equal to B, the standard order. That is the same as saying B minus A greater than or equal to 0. We agree. 4 less than or equal to 5, because 5 minus 4 is 1 greater than or equal to 0. 4 less than or equal to 15. Is that true? Why is 4 less than
Yes.
or equal? Because 15 minus 4 is 11, bigger than or equal to. We know this, but I'm trying to explain this condition. This is the standard less than or equal to. This is a partial order. Is it a partial order? Is 1 less than or equal to 1, 2 less than or equal to 2? Yes. Because 2 minus 2 less than or equal to 2, if and only if what? 2 minus 2 is bigger than or equal to 0. Is that true?
Yes.
That is why. So you see, it is reflexive. It is reflexive. And AB, BA contained in the order, in this partial order. Then now, if AB, if A less than or equal to B, can B be less than or equal to A?
Yes,
This
sir.
partial.
Yes.
Okay, wait a minute. If I'm confusing this with this with this one. If A less than or equal to B, A less than or equal to B, only way it can be equal to A, I have another idea. A and B less than or equal to A means what? This means B minus A greater than or equal to 0. What does this mean?
A minus B greater than.
A minus B greater than or equal to 0. If you have two numbers satisfying this means A greater than or B greater than or equal to A under our usual notation. This means A greater than or equal to B. When B is greater than or equal to A and A is greater than or equal to B, what is it? A equals
A equals B.
B. So it is anti-symmetric. Is it transitive? Of course it is. A less than or equal to B and B less than or equal to C means A less than or equal to C, isn't it? You see, we have a different, this is the partial order relation. This is the standard one. Okay. For natural numbers, if we use the standard order, then it is a partial order, but it is also A less than or equal to B, if and only if A less than or equal to B is a total order. Total order is when any two elements are related. Give me two different integers. Manas there. They are muted, are they? Ishan, how do
Yes,
I
sir.
can I unmute you?
Yes, sir. I have allowed them to unmute themselves.
I need to see you guys once in a while. Is it because of the internet connection?
Sir. Hello, sir.
Yes. Any two elements are related. Give me two numbers.
Yes, sir.
Two integers.
Sir, 1 digit or 2 digit?
Give me two integers.
Okay, 54 and 98.
54 and 98. Are these related under this?
Yes.
Why?
Yes.
What is the
54
relation?
is smaller than or equal to.
54 is less than or equal to 98. Why?
Because 98 minus 50.
98 minus 54 equals whatever is greater than or equal to 0, isn't it?
Yes.
And this, we know all this stuff. What I am saying is that This is a partial order where any two elements are related. Therefore, it is a what?
Total order.
Total order.
So here is an example, like a chain. This is an infinite chain. In the case of D42, we picked up a chain from it, a small chain, 1, 3, whatever, 14, 1, 3, what? 21, 42. But in the case of the natural numbers, the whole set is the chain. Tanish? Yes.
Yes, so like is the set of natural numbers both partial and total order?
Yes.
Okay.
A total order is a partial order. But a partial order need not be a total order. A total order is stronger. Follow?
Yeah, so P implies Q, but Q doesn't imply P.
Right. So that's a good point. It will be in the notes. A partial order where for all AB, either A is less than or equal to B, like this is called is a total order. So it has to be to start with it has to be a partial order to start with. So I gave you an example. Another example is the famous just integers, which are starting at 0, 1, 2, 3, and -1, -2. This also A less than or equal to B under if and only if A less than or equal to if and only if B minus A greater than or equal to 0 will work. Let's see. We know it will work for this one. Will it work for this one? Is -2 less than or equal to is it less than or equal to -1? Is -2 less than or equal to -1 under this? Is B minus A greater than or equal to 0? Is this guy less than or equal to this guy? Is -2 less than or equal to -1? What's the condition? Is -2 less than or equal to -1 if and only if -1 if and only if -1 minus -2 is bigger than or equal to 0. Is that condition satisfied?
Yes.
Is it satisfied? Is -2 less than or equal to -1? Is B minus A bigger than or equal to 0?
Yes.
This is your B, this is your A. Is B minus A greater than or equal to 0?
Yes.
So you see, this works for positive, 0, and negative. This is a partially ordered set. Well, we'll say poset from now on. It is also totally ordered because you can compare any two. We have a homework for you. Okay, and then there is a great principle. I will come to that shortly, called well ordering. There is another order. This is the nicest order. And that's the reason we talked about all this partially ordered set and everything. If you have a totally ordered set, and then if you take, let's call it, yes. If every subset of S has a smallest element when S is well ordered. When you say smallest under, you will find that this class sometimes strange because this is the first time you are dealing with abstraction and philosophy, okay? Probably. I will keep talking in philosophy and abstraction until I get you to think about philosophy and abstraction. When you say something is smaller, you have to have something to compare, don't you? A person may be smaller than another person in weight. So the order here might be weight. Or a person can be smaller than another person by way of length or height. And there are so many conditions, so many different ways you can compare. So anyway, let me give you the last example. If you take the natural numbers, you know what that is. If you take any subset of it, does it have a smallest element?
Yes.
Does a subset of n have a smallest element? Well, intuitively, we feel it has. Don't you agree? If somebody gives you a whole bunch of integers, don't you think there is a smallest one in there? If somebody gave you 10,000 integers, we don't know what they are. They are all positive integers. Don't you think there is a smallest one in there? Yes?
Yes.
We feel, but we cannot prove it. Do you know that you cannot prove it easily? Cannot prove it easily. Cannot prove it easily. That is why there is a principle. This is why we talked for 2 classes, partial order. Well ordering principle. Every subset of natural numbers has a smallest element. This is called a principle because there is no, we don't prove it. We don't prove it yet anyway. We will be using that in the next class to prove. After all, this class is methods of proof. So why didn't we talk about this partially ordered set all this time? Partial order and all that. Because we want to know what a total order is. Then only we will know what a well ordering is. And this has to do with that. So let me see if I can give you a small homework here today. Okay. Yes. Remember I was talking about AB and I said these are the Hasse diagrams of that. A, B, A, B, B, draw the Hasse diagrams for partial orders on S equals A comma B comma C. Okay. I'll give you a hint. Let me see if I have written it down somewhere. How many are there? I need to give you a hint. Because this is a bit of work to do it. Yes. They will all have these shapes. There is one. Things like that. Okay. There are essentially, how many are there? I think there are 19 such pictures. See how many you can find. How many did we do for this one? 3, right?
3.
3. Let us see how many you can find. Let us see how many you can find for when the set has 3 elements in it. There are altogether 19 of them. 19 partial orders, okay? Oh, by the way, this is, I think with this I will stop the class, end the class. Is this a total order? This is a partial order for this set. Is this a total order? What
Yes,
is a
it is.
total? Yes or no?
Yes.
No. A total order is when either this or this for any 2 elements. Agreed? In this case, here is a partial order. Is A less than or equal to B? No. Here A is less than or equal to A. B less than or equal to B. If they were connected, they will be connected by a line going up. I'll give you a small hint. Here, suppose this is A, this is B, this is C. Is A less than or equal to B here? Is B less than or equal to C here?
Yes.
We connect only those. Remember when we were doing D42, we connect only those like that. Only those pairs are connected. So if they are not connected, they are not related. Agreed? A is not
Yes.
related to B. So this is not a total order. Is this a total order for this set? Remember, for a set S, this is a partial order. This is a total order.
Yes, because they are connected.
Yeah, they are connected. All the elements are connected. Either A less than or equal to B or B less than or equal to A. This is true. So here is a total order. Here is a partial order. Is this a total order or partial order?
Partial order.
Why?
Since A is not connected with B.
Exactly. Exactly. Excellent. You understand now, guys, do you?
Yes, sir.
Out of this 19, there are 19 partial orders you can find. Out of this, some are total orders, some are not. Actually, there are 6 total orders. 6 total orders. There are 19 partial orders. But there are 512 relations. Out of that, only 19 is partial. Hey, do you know how I found 512? When you have 3 elements in S, S cross S has how many elements? When there are
6.
3, S cross S has how many elements?
2 to the power 3, which is 8.
When S has 3 elements, S cross S has
8 elements.
when S has 2 elements, S cross S has how many elements?
4.
4.
When
5.
S has 3 elements, S cross S has
9.
how many elements?
9.
9. Then how many subsets does S cross S have?
8.
A set S has 9 elements. How many subsets it has?
5
To the
1
power
2.
9.
2 to
5
the
1
9,
Power
which is
9 which
500 and.
equals 5 and
12.
So you see, there are 512 relations on this little set. Can you believe that? Out of that, only 19 are partial orders. You can draw pictures like this. I want to try to get as many of those 19 as possible. Do you understand the homework now?
Yes, sir.
You may not get all of them. Okay, let's get one more and then stop the class. Let's get one more partial order on this set. Then you get a few more in the homework. You can also try to get all the 19.
Excuse me, sir, Dhru here. I'd just like to remind you that we are 10 minutes over time.
Oh, yes. There is one. Thank you, Rupi. A, B, C. Is it? What does this mean? B less than or equal to A, C less than or equal to A. You check if this is a partial order. And there are other diagrams like that. And you have to label them. This may be A, this may be B, this may be C, or you might have another one where this may be B, this may be C, this may be A, B, C, or C, B. Get it now? These Hasse diagrams are all partial orders. If you are confused, don't worry about it. You get what you can, and we will discuss this in class. Ruhi, can you check the internet and help the students a little bit with the Hasse diagrams for S
Yes.
when it
Yes.
has 3 elements?
Yes, we will do that in the office hours.
Yeah. If you go for the Hasse diagrams, it is easier than if you try to find the subsets of S cross S. Okay? Because there are 512 of those to look for. That's hard. But if you look for the diagrams, it's easier. Okay? So look for the Hasse diagrams and try to pick up as many of the 19 diagrams as possible. Once you get one diagram, by permuting the labels, you will be able to get. I think I gave all of them actually. There may not be any more. This might be all of it. Try to think of it if there are any other. And that is a very efficient way. As a diagram is an efficient way to pick up facets of a set. Okay, because you don't want to try the 512, you can try the 19 assay diagrams. Okay, that's it. See you tomorrow.
Dr. Thomas.
Hello, sir.
Hello. Good evening. I joined 10 minutes after the session started, so I'm not sure whether you got to know that Sai is also volunteering this week. Sai was part of Math Path, I think 3 years ago, right? Sai, or 2 years?
2 years.
2 years ago. And I think it was to Sai and a couple of other students that you suggested that we get in touch and all that. Sai, right, Sai?
Yes.
That's Sai
Our
for
class
you.
is now ended.
Yeah.
Ruhi?
Yes, sir.
Okay, students can go. Vinay, you want to talk to